Hello everyone. Could you hear me and see me well? Let me open the stream link. Okay. Mert is here, Furkan is here. Also Mehmet Ali is here. From our moderators, could you please give me feedback regarding the voice and video quality, guys? Then I will be starting very soon. If everything is fine, can be higher. Okay, let me a little bit increase my volume. Just a second. Okay, I added some a few dBs of increase. Okay, let me also change the orientation of the microphone a little bit. Is it better now, Furkan or Mert? I hope it is better right now. I also changed the orientation of the microphone a little bit. Also, second one is on as well. It should be fine, but what can we do more? Let me check. Just a second. Is it a little bit better now? Better from a minute ago, but you can increase a little bit more. Okay, I increase it little bit more. I think it should be fine right now. Let me check. Let me switch the other one. Okay. I think it is better right now. Let me check. Which one? This HI one. Little bit. I think this is a little bit better. Okay. I have seen the effect right now. It is higher, so I am starting. Okay, great. Thanks Furkan and Mert. Today's agenda is as follows. So we will start to discuss first minimizing number of clock domains in our designs. Then next one is reducing high fan-out nets. Actually, yeah, let me start from scratch. Today we are having actually our second good coding practices and design recommendations lecture. So during the first one, we focused more on reset architectures. In the second one, I added like these 5 topics. I think I have 1 or 2 slides for each one. But first one will be minimizing number of clock domains. This is quite important. Then we will be discussing reducing high fan-out nets, like either synchronous or asynchronous reset nets, or some data valid signals in your design. Third one is preferring block RAMs to distributed RAMs inside FPGAs or SoCs. They are also known as LATRAMs. Fourth topic will be preferring digital signal processing units, DSP cores, to lookup tables plus flip-flops combinations. This is also important and improves resource usage and maximum frequency dramatically. Sometimes, of course, it depends on your design. It depends on your design requirements and design approach as well. Also, of course, yeah, that's algorithms you are trying to implement. And the last one for today will be using compact processes, those process statements in VHDL, and benefiting from generate statements. Also, I added a few remarks regarding for loops as well. We will be discussing if generate statements and for generate statements. Also, for loops have some benefits in sequential designs as well. So I will try to point out those. Then we will wrap up. We have a final slide, and I will check the questions and try to answer them. Also, this Sunday, it will be, I think, 22nd of December. So this Sunday, European time 10 a.m. in the morning, Turkey time like 12 p.m. We will be having a 1-hour Q&A session regarding this lecture. I will try to provide some code examples as well for that one, but we will prioritize your questions. Then if we will have time, if we will have some time, we can discuss some code examples, plus we may review today's slides as well. Okay, the first slide regarding minimizing number of clock domains. So having as few as possible clock domains in your design actually is quite improves the design, let me say, the optimizations from your compiler, your EDA tool, electronic design automation tool. It is getting much more complicated, let's say, much different or much more complicated if you have, let's say, 10 asynchronous clock domains compared to having only one clock domain in your design. So as a general, as an important rule of thumb, try to keep number of clock domains in your designs as low as possible. The ideal one is having only one fast core processing FPGA or SoC clock. So then, of course, you need to decide or optimize that clock frequency depending on your FPGA device family, FPGA vendor and family. Also speed grade. You know, there are different kinds of speed grades. Sometimes for a device family there are 3 different speed grades, and yeah, there is if there is 3 different speed grades for a certain family, then there is a fastest one, the medium one, and the slowest one. So as FPGA design engineer, you need to check which FPGA vendor, which device family, and which speed grade of FPGA is selected, and actually you are using in your system, in your PCB. Then you need to do sometimes some pre-analysis, sometimes some improvement post-analysis. So yeah, it is like more a team decision. It's a team decision. Sometimes it requires also, yeah, you may, for instance, aim to have 2 megahertz core clock in a design, but if design requirements are updated all the time during the design process, you may little bit sacrifice from your aim, and like you may end up reducing it like 10%, 20%. But in general, let's say in ideal conditions, it is really good coding practice, good design recommendation, good design plan to have one fast core processing clock. And it is really important to apply clock domain crossing from low speed peripherals to that fast high speed core processing clock as early as possible. Otherwise, there will be some fan out, some logical operations in those lower speed clock domains, and yeah, it is not preferred because you are adding some logic with some different clock domains and you are increasing the fan out of those clock domains. So it is ideally great to have one fast core clock, and it is great to apply clock domain crossing as early as possible. I gave an example at this point. On the rightmost, at the end of each line, you see the actually regarding processing technology. For Xilinx Vertex 5 family, a 150 MHz core clock is in general a good aim, good target. This is 65 nanometer transistor technology. So let me say 150 megahertz is a good target. Of course, here it is just, it's a kind of generalization. So, you know, all generalizations are to some extent wrong, but this is reachable, doable for a medium level complexity FPGA implementation, let me say. But for Xilinx Vertex 6 family, now processing technology is 40 nanometer. So as you see, clock frequency is a little bit increasing. So also check the relation between the increase. It is like, for instance, 150 to 200 megahertz. Also, like that processing technology is also, you know, you see transistor size are getting smaller. So let's check the percentages a little bit. So from 150 to 200 megahertz, it is like 50 megahertz of increase. So increase is kind of 33%. So let's check the size reduction in processing technology. It is like 25 divided by 65. So kind of also, as you see, 30 something percent. So it is, there is some relation. Of course, it is not linear, but you can relate it. By the way, these numbers, these target clocks are quite doable. As I said, by the way, I worked in lots of FPGA projects during my 15 years of FPGA engineering career. These speeds are doable, and they are not, let me say, impossible to achieve. For 28 nanometer Vertex 7 technology, 300 megahertz core clock, it is also doable. Of course, it depends. Sometimes if you need to do a extremely complex logic, you need to implement, then, for instance, you may reduce clock speed to 150 megahertz, so divided by 2, and use a clock enable or data valid signal for that case. And you need to also apply multi-cycle path constraints for those complex logics. So these stuff are doable. In case you need to achieve, you need to implement a logic whose periods cannot be 3.3 nanoseconds, and you can do it with multi-cycles, in multi-cycles. But if it is possible, of course, it is preferred to have 300 megahertz clock speed for that Vertex 7 example in all logic in the design. So for the ultra scale, Xilinx ultra scale family, now it is 20 nanometer technology, and now target clock is 400 megahertz. Also for ultra scale plus, 16 nanometer technology at 500, 450 megahertz, kind of those clock speeds are doable. For the newest generation adaptive system on chip modules, Versal FPGAs, SoCs, actually they are not FPGAs right now, they call them adaptive SoCs. Their technology is 7 nanometer and 800 megahertz core clock is achievable. So it is like a target plan. Of course, it may, those frequencies may, you may little bit sacrifice, like 10%, 20% sacrifices are fine. But in general, motivation is like that. As you pay more for the technology, you need to improve your clock speed, and you need to actually optimize your design according to those newer technology families resources. So this is a key point. Next one is reducing high fan-out nets. Actually, yeah, this is also an important remark, important good coding practice. You need to reduce those high fan-out nets as much as possible, because as the fan-out increases, if, for instance, you have a either synchronous or asynchronous reset signal, let's say an asynchronous control signal whose fan-out is like 20,000, then routing congestion starts. Also, since this example was for an asynchronous reset, then you start to get some negative recovery slacks. If it is a synchronous reset or another synchronous control signal, then you may end up with some negative setup slacks. So those closing the timing, so, and also closing the timing is getting harder. So timing closure takes more time. Also, you may end up with negative slacks, so timing failures at the end. Plus, placement and routing of your HDL design, HDL codes, getting harder and harder. So there are many techniques actually handle this high fan-out nets. I added a nice documentation from AMD Xilinx high fan-out net optimization techniques. I will share the slides. You may check this web page. Also, there are similar ones from Altera, Intel Altera as well. Yeah, like, let me say, one of the first things that is coming into my mind is you are sometimes limiting to fan-out to, let's say, to thousands, and then those nets, in case of high fan-out signals, compiler applies some optimization and duplicate those registers and try to solve that high fan-out problem by using some extra resources. This is one of the simple solutions. Actually, there are like moderate solutions. Also, there are some advanced solutions as well. So it depends on your, again, your technology, the technology you are using, your coding style, the algorithms you are trying to implement. So there are many things affecting the results of such solutions, and actually there are many variables regarding those problems, and there are many different ways of solutions. So yeah, at FPGA and SoC design, and also of course it is verification, it is quite complicated. For me it is quite exciting, but complicated as well because you are doing transistor level design. So it is low level design. There are many pros. You can achieve high throughput with extreme low latencies compared to fasted CPUs or GPUs available in the market, but one of the major trade-off drawbacks is those design and verification cycles are longer. So of course, for each, as I mentioned before, for each kind of chip, there are some pros and cons you need to be aware of. Them. So this is the reset signal. Only when it is a must. We covered this topic in detail during the previous lecture. So you may, if you haven't watched that one yet, you may check good coding practices and design recommendations. First lecture. Yeah, this also like high reset. If you either synchronous or asynchronous resets, if you are increasing fan out of those resets, then you are getting, if you are resetting signals that are not supposed to be reset, then you are increasing the fan out of that reset signal. Same story that I explained a few minutes ago. Timing closure getting complicated, takes more time, and sometimes it fails also. Placement and routing is getting harder, and sometimes it is not doable. But the key, one of the key remarks to solve these issues, you need to master your FPGA vendor. Let's say it is either Altera or Xilinx or the other FPGA vendors. You need to master the device you are using, device family, and actually the exact part number includes speed grade as well. You need to master the chip your company provides to you in that, for that particular project. Let's say you need to read its documentation and you need to apply some edit, compile, and check the results kind of cycles. So it is not that easy to optimize some resource usage. It is not that easy to improve the maximum frequency. So you need to edit your codes, your designs, compile them, check the timing results, check the resource usage, and you may need to do some this kind of cycles to end up with the optimum design solution for your algorithm, for using the particular FPGA device or SoC device. And it is pretty important. I also mentioned this during previous lecture. I gave some nice results with some Altera and Xilinx families. Using built-in device resources matters a lot. So then you can, you will be using much less device resources because you are using some built-in ASIC features. Fmax will be higher, and you can pack more complicated designs into the same FPGA or SoC. So this is quite important. Next one is preferring block RAMs to distributed RAMs, also known as LUT RAMs. This is also quite important because sometimes if you don't specify, compilers like Quartus, like Vivado, like Libero, if you don't provide any constraints, they are sometimes using distributed RAMs, but sometimes they are using block RAMs. So if you don't constrain the tool, so to optimize timing and to optimize resource usage, these tools are making some decisions according to their own algorithms. So in general, it is a good coding practice to prefer block RAMs to distributed RAMs, because those slices containing lookup tables and flip-flops, they are more preferred for some to implement some processes in your design. But for the storage, most of the time, you preferring block RAMs is much more favorable, because you need to, for some if statements, for some case statements, for some decisions, you need those lookup tables and flip-flops inside the slices. Xilinx call slices that to the design elements that includes lookup tables and flip-flops. Altera calls them ALMs, adaptive logic modules. So the lookup tables inside those slices slash ALMs, as I mentioned, include lookup tables. They might be used as random access memories, RAMs. They are called LUT RAMs or distributed RAMs, but they are, to my experience, for instance, I had the preferred LUT RAM usage in the past, just for a specific project which requires a local fast logic implementation, because those LUT RAMs are implemented in slices. If they are not huge, you can benefit from that LUT RAM technology to achieve higher clock speeds. But other than that, most of the time, like 95% of the time, block RAMs are good enough. And VHDL attributes or Verilog attributes, SystemVerilog attributes, actually the attributes I am mentioning here are dependent on vendor. They are kind of vendor specific attributes. So they are provided inside, examples are provided in Vivado, Libero and Quartus documentation. But for instance, RAM type attribute is a nice one. Actually, they are named as HDL synthesis attributes. So you can use, after your architecture definition, before the begin statement, you can add some attributes to force preferred RAM type. For instance, it is, I am mentioning here usage of the plain VHDL, not using IPs, macros from IP library of EDA tools. That is also doable, but in general it is not preferred. Plain VHDL is plain VHDL, Verilog or SystemVerilog is preferred for design, because using components from IP libraries and calling those components is reducing readability and reusability. That's why plain VHDL is preferred most of the time, especially for experienced HDL FPGA engineers. In that case, you can use those RAM type attribute, this RAM type attribute, to force block RAM usage, for instance. This is a good coding practice. Next one is preferring DSPs to LUTs plus flip-flops. Arithmetic operations like multiplication, subtraction, multiply, and accumulation, some pattern detection, etc. These stuff are doable by slices or ALMs as well. But digital signal processing blocks, DSPs, are actually the ASIC macros, ASIC designs, applications for this arithmetic logic purposes. So try to, and this is of course in addition to those arithmetic operations, there is, as you see here, this is an AMD Xilinx DSP58 figure. As you see, there are many pre-registers and post-processing registers at the output side. So actually these DSPs includes many multiplexers as well. You see there are some muxes and extra features that is tough to a little bit guess just by checking this figure. You need to read its documentation, their documentation in detail. But some of them are, you know, as you see, easy to see. Multiplier 727 bits by 24 bits multiplication, and output is unlike most of the previous generation, older FPGA generations DSPs, output is 58 bits. Previous generations were more like 48 bits. So you see those pattern detection feature is there. Some carry inputs, negation stuff are doable, and those pre-registers, two level of preliminary registers and post-processing registers, here you see on the right side, they incredibly improve the maximum frequency, and using just a few DSP 48 or 58 slices or ALMs in the design. Because if DSPs are not preferred, actually if you don't write your plain VHDL codes or plain HDL codes in appropriate way, tool cannot fit your design into these DSPs and automatically uses lookup tables and flip-flops. Then those slices are kind of wasted, because much remarkable solution possibly available using DSPs. So using the feature of these digital signal processing cores are quite important. Also, if your coding style, your coding template, your design approach is fitting with your FPGA family, your SoC family DSP structure, using that multi-style attribute is also possible to force preferred multiplier usage, for instance. In the past, one of the, for instance, ARIA 10 FPGA families, I was able to, in some of those ARIA 10 projects, I used multi-style logic because all DSPs were used. Actually, there were not enough DSPs in a particular project, but in another one, since many DSPs were available, I prefer that multi-style attribute and force it to use DSPs. And then, yeah, I could, for instance, in the second one, I could achieve higher clock frequencies, a higher clock frequency, and implement the algorithm easily. Of course, this stuff depends on the legacy designs you have and actually intellectual properties you have in your team as well. There are many variables, many dependencies, but yeah, knowing the built-in resources of your IC family matters a lot. So this is an important remark. Okay, the last one is using compact processes and using generate statements. Actually, I see, for instance, I am also doing some HDL reviews from the some of our channel members are sending me some HDL code and asking me to review. I sometimes see yeah, instead of dividing and conquering an algorithm and using, let's say, 3 or 4 processes, they are just writing a 1 or 2 long processes. I am mentioning here process statements, sequential process statements, let's say in VHDL. Actually, the motivation shall be keeping processes compact, so short, and they shall be dedicated to a specific job. If you add all those statements, sequential statements into one process, then EDA tools, I mentioned those EDA tools, Vivado, Quartus, Libero, and the others, they are getting confused because you are adding all those sometimes dependent, sometimes independent statements into just one process. Then those tools cannot optimize, cannot map your hardware description language statements into its resources, like those DSPs, LUTs, lookup tables, flip-flops, multiplexers, distributed RAMs, block RAMs, etc. So those processes shall be as short as possible, and if statements doesn't have any relation, then they shall not be in the same process. So you need to divide and conquer and make improve your state of mind regarding those code writing techniques. Of course, it will help a lot if your team members, your team leads review your codes. Then this period of improving your coding styles will get much shorter. That using FPGA vendor and family specific coding types is quite important as well. Actually, in Vivado, in Libero, and also in Quartus, there are some nice code examples. So they provide some templates, then use those vendor dependent, family specific design guidelines. There are some also nice documentations. Read those and use code templates that will help producing optimum designs a lot. The last one for today is benefiting from if generate, for generate statements and for loops. Actually, these three three statement types improves readability and reusability a lot, because your instead of, let's say, having 500 lines of code, with this usage you are doing it just in 200 lines of code. So this stuff shortens your repetitions and improves your readability. I will, for instance, if you have a generic design which provides some optimum solutions for different families of an FPGA vendor, then if generate statements helps a lot. Then you actually select and run the VHDL lines that is specific to a device family. For generate statements are also sometimes quite helpful, because you are doing a for loop and generate it accordingly depending on some constant or some generic value, some constant from higher level package, or some generics again from higher levels of hierarchy. For loops are also fine. Don't scare about the usage of for loops. Sometimes instead of writing the same code like 10 times, just a for loop starting from 0 to 9, it applies the same stuff. So again, you just in 3 lines you solve it instead of repeating same assignment 10 times. But of course the limits shall be clear, and also the range of for loop it should be proper. For all these three, if generate, for generate, and for loops, you need to take care of the indexing stuff as well. So depending on your loop parameter, you need to assign those, make those assignments in a correct way. It is not tough, but a little bit hard to explain verbally. I will try to provide some code examples during our Q&A session on this Sunday morning. Yes, this was all for today. So the end of our 11th lecture in our in English FPGA from Zero to Hero series. Thanks, and hope to see you on Sunday morning, sorry, 22nd of December 2024. Now I will check if we have any questions in the chat box. Give me a few seconds. I would like to refresh my coffee, drink a little bit, and I will check the questions very soon. Let me make my camera view to full screen, and now I will check the questions. Okay, for today we have some nice comments, some highs, and some feedback regarding to video and sound quality, and but we don't have any questions. Hoping to hear some questions during the Q&A session on Sunday. But unless you have any questions, I will review the slides briefly, and I will comment about the code examples I will prepare. So thanks a lot for attending and listening today. Wishing you a great evening or night for the ones close to European time zone. And if we don't see each other until next year, have a great new year as well. Take care and bye bye.